In this video we're going to discuss our spring systems. So let's imagine a spring connected to a board, and we're going to look at horizontal springs. This will also apply for vertical springs, which you'll be looking at in your lab. So we have some mass, and let's say that this mass has been pulled out. Here's our 0 point. We know that there is going to be a force of the spring that's going to want to restore the mass to equilibrium. And if we were to compress the spring, again, there's a force on the spring that's going to repel the compression. It's always wanting to go back to its equilibrium point. So this is Hooke's law. And Hooke's law is expressed mathematically as the force of the spring is equal to negative k, some spring constant, times x. And this spring constant k is specific to each spring. And it's based on what the spring is made of, the density of the material, a bunch of different factors. Now, let's look at how we can describe the motion in a spring system. What causes the oscillations? So let's take a look at this mass. This mass is going to have a force, and our mass times, now we know mass times acceleration is a force, but think about this. This mass is going to be traveling, and it's going to slow down, and then it's going to stop, and it's going to go in the opposite direction. And as it goes in the opposite direction, the acceleration is going to change. It's going to get to the equilibrium point here, and momentum is going to carry it past that point. And so it's going to go to the other side and stop, and then head back towards the equilibrium point. It's going to continue to do this. Remember, we're talking about frictionless at this point. So our acceleration is not constant. It is a function of time. And that's going to equal the sum of our forces as a function of time. Well, we know that the acceleration is the second derivative of distance. And we have Hooke's law, which is negative kx, and I'm going to put x as a function of t. And now we can simplify, move everything over to one side, and move our m's around, and we get second derivative with respect to t of x of t plus k over m x function of t equals 0. We solved a very similar equation. Of course, this is a homogeneous equation. And so we solve this by using a test function. We'll call it the homogeneous. And we're actually using a function x. So used to writing y's after the differential chapter. And we use something in the form A, E. We used R previously, but for reasons that are going to become known here shortly, I'm going to use omega t. And when we put this into our differential, we can take the double derivative, second order derivative. That's going to be A omega squared E to omega t, and then just write the rest of it here. Now the a's are going to cancel, the e to the omega t is going to cancel, and I get an equation, omega squared plus k over m equals 0. So omega is going to equal plus or minus the square root, actually forgot my j here. We'll just look at the positive root for the moment. So j times the square root of k over m. And remember from our previous dealings with differential equations, we know that this has to have a sine and a cosine, and so our general formula, x function of t, is equal to c1 cosine omega t plus c2 sine omega t. At times we don't want to have to deal with both trigonometric functions. We would like to be able to put these into one cosine function. And so let's say we want a function some amplitude times the cosine omega t plus some angle shift. And we want to relate that back to this equation. We can do that by taking the cosines, the addition of cosines, and if you look at the trigonometric reference, we see this formula right here. Notice it's cosine cosine minus sine sine. So we're going to have a cosine omega t cosine phi minus sine omega t sine phi. And that means that we can rearrange this in a little bit different form. A cosine phi cosine omega t minus a sine phi sine omega t. And that just means that C1 is going to equal a cosine of phi, and C2 is going to equal negative a sine of phi. So now we need to solve for a and for phi so that we can get the conversion between the two. And to solve for a, we could take the uh, square of both of these. So we have c1 squared is equal to a squared cosine squared phi, and c2 squared is equal to a squared sine phi. And if I add these two, and we can pull out the a squared, and cosine squared plus sine squared is 1, so I have a squared, and that means that a is going to equal the square root of c1 squared plus c2 squared. And now to get phi, I can take and divide Okay, now I have a tangent function. The a's are going to drop out, and the negative sign I'm going to move to the other side. So I have tangent of phi is equal to negative c2 over c1, and phi is just going to be the arctangent of negative c2 over c1. So we can rewrite this in terms of the other equation, square root of c1 squared plus c2 squared cosine omega t plus the arctangent of c2, oh sorry, should be negative c2 over c1. So each of these equations are equivalent. And this is how we describe the motion or uh, the oscillations in time for a spring. And x then is either positive or negative, and if we look at the spring, we have some equilibrium point, and this could be x positive on this side, and this side would be x in the negative direction. So in the next video we will look at some of the different properties of the spring and how we can calculate the velocity and the acceleration.